as a brief overview, we're going to talk about modal testing, and this presentation is more about why and how we conduct a modal test and less about maybe some of the theory behind it. Let's just dive right in, and let's say we're presented with this question. So we are working as structural analysis test engineers, and now we got to conduct a modal test. And somebody in our lab has handed us this kind of odd shaped hammer that doesn't look like a traditional hammer we've used in the past, or a structure, and they're saying, I need you to find the first or second mode of this particular structure. And so how do we go about that? Well, we need to determine natural frequencies and damping and mode shapes, and we're going to talk about that a little bit today. But a natural frequency is something that once we put energy into a system, it's a frequency at which that system wants to let go of that energy. And when it lets go of that energy, it moves in a specific way, not always noticeable to the naked eye, but it moves in what we call a mode shape. So we have this jet here, and we're looking at a mode shape on the right-hand side after doing a test. So let's talk about these three things really quick. Let's talk about what that test setup would look like to get these mode shapes, how we would execute that test, and then what we do with that data. So for the test setup, there's some things that we need to take into account. And these are those things. So what are our boundary conditions? And we'll talk about what that means here in a minute. The driving points, or how and where are we going to excite this structure? And then what kind of force method are we going to use to excite this structure? So once we have a driving point, we're going to input a force at that point, and we have some options there. Are we going to use an impact hammer like we mentioned in the past here, or are we going to use a shaker? And then the force level, we have some different options there, even more specifically with that impact hammer that we talked about, and how that force selection behaves based on the linearity of our system. So these are the things that we're going to talk about first. Okay, so boundary conditions. It depends on our goals, is the point here of this slide. So real boundary conditions, if we look at that as an example, most of us are familiar with an automotive vehicle, and on an automotive vehicle, we might have different components. We might have like an exhaust system, and if we took that exhaust system off the car, the boundary conditions would be different for that type of test if the exhaust system was just hanging on a hanger or from some bungees or something, as opposed to that exhaust system actually being bolted into the vehicle when it was sold or in a driving condition. And so those real boundary conditions would be the example for that exhaust system being bolted to the vehicle. And when we have these real boundary conditions, we might be adding some stiffness or some damping, and we could be adding mass. If you think again about that exhaust system, when it is attached to that vehicle, it's obviously got some stiffness associated with it, with the bolts and the exhaust hangers, and there's obviously some different mass because of the way it's attached to the vehicle. But that data is still useful if we want to look at the modes being caused by that exhaust system when it's in its actual environmental conditions. But if we want to do some correlation to, say, a CAD model or some analysis that's been done, we might want to use something referred to as free suspension. So a free suspension means that we're going to put this structure on some kind of maybe bungee cords or pneumatic suspension with some airbags. It'll help with that correlation. And what we can really get from that too, if I add a laser pointer here, is some rigid body modes. So in that analysis, those rigid body modes will all be at 0 hertz. And those rigid body modes are the translational modes or translational movement across the axis. And we'll look at those in a second. So there's going to be 6 rigid body modes, right? There's 3 translational and 3 rotational around that XYZ coordinate axis. And like we mentioned before at simulation, these 6 rigid body modes will all be at 0 hertz. And the test, it depends on how well we've done in that free suspension, how well we've put it either on bungees or a pneumatic airbag. So here's kind of those setups, the way they look. So we have, this engine block here on some bungee cords. Pneumatic suspension would be something like this, where we have these airbags to kind of more or less levitate the structure. So this large plane here is on a bunch of different airbags to get that. And you can see that here's a zoomed in picture of the landing gear on some of these airbags. And then here's another smaller plane on some elastic bungees as well. So you can see the three points that would touch the ground, the three parts of the landing gear are on those bungees. And these would be examples of free conditions, okay? And we want free conditions, again, to correlate to FEA. That's where we want to start and stop when we're doing this correlation. And here's an example of the rigid body modes. So this is actually from analysis, and we can tell that because the frequency here is at 0 hertz. But a rigid body mode would be a translational or rotational movement of the structure where all of our measurement points are in phase, moving together across those 3 axes. A flexible mode is where we start to see some bending or some twist or some movement based on our points, where the points are going to be out of phase from each other to show how that structure is bending or flexing at a given frequency. Okay, so here's a good example of what a rigid body mode or a flexible mode would look like. And again, these rigid body modes in our physical test would only become apparent in a free condition. And normally in a test, these rigid body modes occur at less than 10 hertz if we've done a good job setting up our free condition. So let's talk about driving points. So now that we have this test or this structure set up in a free condition, now we want to pick the point of excitation that's best. And so a driving point is where we're going to excite and measure. So right here in this example, I've got a hammer and an Excel. And as long as I hit this hammer at this specific point, that would correlate to a driving point. So we have a different graphic here to represent that. And we can see I've got points 1, 2, and 3. And these points 1, 2, and 3 would be where I have accelerometers. And so I've got response degree of freedom. And so along what we're making here is what's called a modal matrix, okay? And if I hit with my hammer at location 1 and get that response at location 1, then that would be my driving point, which would be hammer 1, Excel 1. And so when I make this matrix, the diagonal of the matrix is going to be my driving points. So in other words, I've got hammer hit and Excel at location 1, hammer hit and Excel at location 2, and hammer hit and Excel at location 3. All right. And you can see in terms of driving points, I'm exciting all 3 modes that would correlate to this simple beam. I'm exciting all 3 modes with a driving point at location 1 and a driving point at location 3. Okay. So location 3 or location 1 would be the best points to excite my structure. Okay, those are my driving point FRFs. Now, when we go to test our structure, a lot of times we'll do something called a driving point survey. All right, and so you can see by doing a driving point survey, I can get some different locations. Okay, so we've got 1 good driving point and 1 bad excitation point. So if I was going to conduct my test, I want to do this driving point survey, kind of like what we did in this previous slide. We hit and measured at 3 locations, and this would be more emblematic of an actual structure where we're going to get a bunch of modes, and I look at a bunch of different driving points, and I can tell that the green one is a good excitation point because with the bad excitation point in the red, there are 2 modes that are not being excited when I input a force, okay? So this is kind of how a driving point survey would go. Let's say we have this simple plate, and I've got my accelerometer and my hammer at one specific location, and we call that FRF point 1. And I find the modes here by measuring that. And then I go to point 2 with both my hammer and Excel, and I see some modes again, and I continue to do that. And let's say I take a driving point survey of 6 different points. And Charles, if I were to ask you what would be the best driving point for this particular structure, what would you say?
I'm putting my money on 6, Scott.
Yeah, absolutely. It'd be 0.6. And the reason Charles is picking that is because if you look at FRF 0.6, I've got 5 modes here that are excited, whereas in the other ones, I don't have as many peaks or as many modes that are excited by that force input. Okay, so 0.6 is right. Now, how do we want to put this method of force in? Well, we've talked about impact hammers so far. There's also shaker testing. Okay, so with hammer testing, we've got different size hammers depending on how much force we want to put into a given structure, and potentially what frequency range we want to look at as well. The larger the hammer, obviously, the more force I can put in. But again, the larger the hammer, I cannot go as high in frequency. So with these two large sledgehammers, I won't be able to look out to a high frequency range. And we'll go through some things in the software to kind of determine where we can look and the frequency range selection based on our hammer setup. We'll talk about that too. The nice thing about a shaker is I can take shakers and put those at multiple locations. So for example, on just this brake disc, you can see there's 2 inputs, 2 different shaker inputs. But I can set that shaker up and I can tell it what frequency to excite or what range to excite based on some software settings. And then that force input will be put in based on what I tell it with the software. So we also have something in our software called MIMO shaker testing. MIMO, the abbreviation there is multiple input and multiple output. So if we have a shaker and we have a relatively small structure, then maybe I only need 1 shaker. And in this case, this large shaker might even be overkill for something that's like a toy truck. But if I have this actual mining truck here, and if you guys have ever seen these in person, these are basically the size of a 2-story apartment building on wheels, but they're large. And I don't think 1 shaker is going to be enough to excite this structure appropriately for me to see all the modes. So we might want multiple shakers here. And if I have multiple inputs, I'm going to get multiple outputs. But I can set up 2, 3 shakers here and get the force into this vehicle at different points. And then I can get that test or that modal matrix to analyze a lot quicker. If I want to stick with hammer testing, I can still use a hammer, but like we talked about before, we're going to want the appropriate hammer for the job. And in this case, we have this hammer. We're looking at low frequency for this large object. We're going to need a big hammer. So this is actually a video of Charles and I on site doing a demo of our software. No, just kidding, it's not. This is a video that we got from one of these mining trunk companies where they're actually doing an impact test. But because it's such a large structure, they need a large hammer to get the appropriate amount of force in. Okay. So we've talked about some shakers a little bit. Let's dive into that hammer a little bit more. If I've got various tips for my hammer, what tip should I use? So if we have an impact hammer, a lot of times it'll come with different types of tips that I can screw onto the hammer tip here. And this is a steel tip. This is a rubber tip, and then there might be some nylon tips as well. And the reason we have different tips is based on the frequency range that we want to excite, okay? So we've got 3 different tips here on a hammer, and they're all exciting the same structure. And you can see the legend here. The red is the response function, the FRF, and the green is the coherence, and the blue is the input force. Okay, so we have the input over output, that's our FRF. Sorry, we have the output over input, the acceleration over the force for our FRF. And if we look at this, the blue line is our force. So for a metal tip, we get a good excitation out to 5,000 hertz. Nice flat line, that's what we want. For the nylon tip, we get a pretty flat line, and then we dip before that 5,000 hertz and it really trails off. And if we look at that rubber tip, down here at the low frequency, we get a higher amount of excitation than both of these two, but it trails off a lot quicker. The main takeaway here is that with the softer tip, the higher the amount of force at the low frequency. With a harder tip, the higher in frequency I can go with the excitation, okay? And that's evidenced as well by the coherence. We haven't fully talked about the coherence yet, but the coherence is a measure of the amount of force in versus the amount of force out. So we want that coherence to be a 1-to-1 ratio, meaning all the force going in we want to measure, and if that's the case, it stays at 1. And there's reasons for it to dip like it's doing here. It might dip there based on a anti-resonance or a point where there's no energy measured at a given mode. And the way to think about that would be, say, like a second or third bending. There's points that aren't moving at that mode that are basically like flex points that you could think of, or an anti-node. And for the most part, with this metal tip out to 5,000 hertz, we have a good coherence. But if I go down to the rubber tip, where we see that drop off in the force excitation, you start to see this coherence get a little ratty or a little jagged. And it's definitely not getting up to 1. So there's some force there that's not being measured. It's not being excited enough by what we're putting into it to get that coherence level up to 1. So the big takeaway here for this slide is lower frequency, I want a softer tip. Higher frequency, I want a stiffer tip. All right, linearity. So one question that Charles and I are asked often when we talk about modal testing, often with a impact hammer, is how do I ensure that I'm always putting in the same amount of force to get the right measurement across my averages? Do I need to get a robot that will hit the hammer exactly the same way every time with the same amount of force so I can make sure that my measurement is good? Well, the reason you don't need a robot to put the same amount of force in every time is because of the linearity of the FRF. So we briefly mentioned that the FRF is the acceleration divided by the force. So it's a ratio. And if I think about it in terms of a ratio, the amount of force I put in, if I put in a lot of force, I'm going to get more acceleration with my accelerometer, right? I hit it harder, there's going to be more vibration. I hit it lighter, there's going to be less vibration. But the ratio, based on the linearity of the system, will stay the same. And that's what this slide is showing. So here on the left, we've got 3 different force inputs, okay, at varying levels. But my FRFs for those 3 inputs is line on line, okay? So it's good news for us as human beings not being able to hit with the exact same amount of force every time, that the linearity and the ratio of what we're measuring will carry over. So the takeaway there is that as long as I hit consistently, not necessarily at the same force, but at the same location and in the same manner, I should get consistent FRFs, okay? Now there are sometimes, in this example, we've got 3 different force levels again, and the result here, if you look at for the high, there's a little bit of a difference here in this mode. And sometimes that might happen because I don't have things tightened down correctly, or my boundary conditions are a little off. So say, for example, in this particular graph, when I hit it with a high amount of force, I might be hitting a rattle or exposing a bolt that's not tightened all the way or something like that. And that might change my structure a little bit. So that might lead me to check for some rattling or loose parts based on knowing that I should have a linear system here with what I'm testing. Now there are cases in modal tests where there is non-linear systems that we're looking at, and a good example there would be a rubber component like a tire. Obviously with a tire, depending on how much air is in the tire or the loading condition of the tire, the structure changes, the stiffness changes. Some kind of engine mount or structural mount may also be an example. Depending on how much load that rubber part is under, the linearity of the system will be different. And in that case, what we're talking about doesn't necessarily apply. But for most systems, the good news is that we're testing linear systems. And so this ratio, this acceleration divided by the force input, allows us to get consistent FRFs with the hammer hits that we're doing. Okay, so test execution, let's talk about that now. So now we've done some setup. We're ready to take some test data. We've kind of planned for everything. Now we need to actually mount these accelerometers. We want to manage the points that we're measuring. We'll talk about that a little bit. There's this thing called roving hammer versus roving accel. And then we also want to make sure we're getting good quality FRFs and how that coherence is related to that. So when we mount accelerometers, a lot of times we'll use the right-hand rule. Okay, so the right-hand rule is kind of graphically illustrated here. In our software, you can add this column in the channel setup called the multi-channel, and then it will account for your triaxial accelerometer. So what that allows me to do is just set one direction, and it'll take care of the other two. So if I can't set up my accelerometer in the traditional XYZ configuration, maybe I have to turn this accelerometer on its side to get it where I need it to get it, the wire's in the way or whatever it might be. If I have to put, say, that accelerometer in the negative X direction, it'll account and say, okay, that means the Z is -2. And the nice thing about that is I don't have to go through and correct my directions of my accelerometers after the fact to make sure the phase is correct when I look at these mode shapes. It's nice to have something that's looking out for me going into the test as well. So that helps with that test setup and execution. Another thing we want to take into account is a lot of times when we're mounting these accels, they might not be on a perfectly flat surface. We're trying to keep that XYZ coordinate system consistent. We can use something like an angled block or maybe a piece of clay if we're looking at low frequency to kind of make sure that accelerometer is in the right configuration of that XYZ coordinate system. We don't necessarily want to introduce an Euler angle or some weird tilt to our accelerometer when we're mounting it to our structure. And things like this will help us with that. Let's say we've got a frame or we're measuring a body. One of the things we want to keep in mind is how we organize our points. So I've got this symmetrical structure, and as I move accelerometers, I don't necessarily want to crisscross wires as I mount the accelerometers, or if I've got multiple channels, I want to keep track of where these accelerometers are laid on the structure. And what we're kind of trying to illustrate here with this slide build is that, I want to keep, say, channel 1 and channel 2 on the same side of the vehicle. That allows me to move from one point to the other without kind of introducing this additional confusion as to where my points lie. Another good example of that from my past experience is if you're doing, say, again, working on an automotive vehicle, if you're doing a full vehicle modal, you might have 100 to 120 different accelerometers that you're putting every which way upon this vehicle. Or if you think back to that large plane when we were talking about the free suspension, if I'm putting 100 or 200 different triaxial accelerometers on that structure, I need to have a method that's going to help me lay these channels out. I don't want channel 1, say, on the right wing and channel 2 on the left wing. I might have channel 1 and 2 on the right wing, or the first 50 channels on the right wing and the next 50 channels on the left wing. I gotta have some way of keeping track of where these channels are in case the channel goes bad or I get a poor FRF measurement. I need to know where that is, and it helps to have some kind of plan to lay these accelerometers on a structure. Okay, let's talk about roving hammer and roving accel. So one reason that impact testing is prevalent when we do modal testing is it's a quick and fast and easy setup. I can do a full vehicle modal like I just talked about, even though I have done it in the past with 100 accelerometers. If I've got the time, I could do that same test with just one triaxial accelerometer and a hammer. I can just rove or move that accelerometer, 100 points, 100 different locations to build this modal matrix. So when we're doing a modal test, we want to build a modal matrix, and the more complete this modal matrix is, the more complete or the more in-depth of a modal analysis we can do. But if I just want mode shapes, I just have to complete one row or one column of this given matrix, okay? And you can tell here I've got this hammer, and we're gonna do this simple plate, and we're gonna look at 9 different locations, and we've got, you know, maybe just one Excel and one hammer. But ultimately what I'm gonna do is build this 9 by 9. I'm gonna try and strike with the hammer at each of these locations and measure with a triaxial Excel at each of these 9 locations. So just like we had with that simple beam earlier in the presentation, when I hit this first location, I've got force 1, but I'm hitting in the Z direction, okay? So I'm hitting down with the hammer. So I'll get force 1 in the Z direction, and I'll get a response with my triaxial accelerometer at these first 3 points. I'll get a triaxial accelerometer measurement at 1 X, 1 Y, and 1 Z. And then I can move this hammer and I can hit at the corners, and I'll get my X and Y locations. So just by hanging out here and tapping with the hammer in 3 locations, I'll fill out this first 3 by 3 matrix, okay? So like we said, we can get a modal analysis with 1 row or 1 column to start calculating mode shapes, okay? And just like I said, if I hit in the Z direction, I'll get my responses, okay? So I'm gonna move my accelerometer. I'm just gonna hit in the Z direction. I'm gonna move this accelerometer to each of these 9 locations and complete the first row of my matrix. So I could do modal analysis right now. I've got 1 complete row. And the way that I did that was roving the accelerometer, okay? Now, if I rove the hammer, so I'm just gonna keep my accelerometer at this location now, and I'm gonna hit in the Z direction 1 through 9, I'm going to get this part of my matrix filled out. So I hit point 1, and then I move my hammer to point 2, I get that one, and I move my hammer to point 3, and I get this one. Now the problem with this is I've got some gaps in my matrix, right? I've got to go back through and I've got to hit in the X and Y direction with my hammer at each of these locations. Now, the problem with that is once I get, say, to this 0.5, I can easily hit in the Z direction, but there's no easy way to hit in the X or Y unless I add some kind of post. If I add a post, I've changed the mass and the stiffness of my structure because I've had to weld or bolt something there. And I've also added this mass in the middle of my structure. So I've already changed my structure. I'm not going to get an accurate analysis by doing that. So a lot of times, kind of my personal recommendation is to do a roving accelerometer because it's easier to move that accelerometer and measure those 3 degrees of freedom without having to alter my system at all. Okay. But that's the difference between roving hammer and roving Excel. Now, quality check, make sure I'm getting good FRF functions. I can check that with my coherence, okay? I wanna make sure my coherence is nice and flat, equal to 1, meaning the energy in is being measured out. The energy being measured with my accelerometer versus the energy in, we want that to be 100%, okay? We don't wanna measure other forces based on something not being put into the structure, okay? So let's actually do a little bit of a modal test. We'll start kind of clunking around and talk about how these things work in the software in terms of what we're looking at. So what I have set up, we're going to kind of stay with that simple plate structure. Okay, so I've got 6 geometry points here. The nice thing in the software here, I'm just going to use 1 impact hammer. So you can see I've got a force and an Excel ready to go. And I'm going to do, I'll stay with a driving point. We'll measure table 5. All right, so I can click on this and say, this is where I have my accelerometer and my hammer to start. And I'll label it that way by saying insert. So both my accelerometer and my hammer are going to strike this particular location. And I've got that set up here. Then what I'm going to do is I'm going to jump all the way to impact setup. And what we're going to do here is we're going to set up something called our trigger. We're going to look at our hammer tip, see how that works. We'll talk about windowing and then that driving point survey that we've mentioned in the presentation. So first I'll do trigger. I'll say start scope. and you'll hear me tap on my structure here. Varying force levels. And then I'll hit stop scope and I'll apply suggested values. So based on those hits that I did here just a second ago, I'm going to apply some suggested values. And by doing that, it's already told me what my input range should be, what my trigger level should be, and what my pre-trigger should be. And let's talk about what these mean. So the trigger level, I'm actually going to raise a little bit, and that's this black line. And what this is saying is that it will not start to take data or recognize that a force has been put into my structure until that force level comes up and crosses that black line. So once it does that, it knows, okay, there's a force input, I'm going to record data. Now, the downside of waiting for it to record data until it crosses that line, if I zoom in here, okay, so this is our force curve. As that force ramps up, I'm going to miss this first part of my force input if I don't have a pre-trigger. So this black line, this vertical black line, corresponds to our pre-trigger. And what this is saying is, once I've crossed my trigger level, I'm actually going to go back in time and write to disk this amount of time data. So I capture the full ramp up of that force and the full ramp down. If I don't have a pre-trigger, if I had a pre-trigger of 0, okay, it'd be about somewhere, well, I can just type 0. Okay, and then we'll zoom in here. So if I have a pre-trigger of 0, no pre-trigger at all, I've missed all of this force input by not having a pre-trigger. So when I have a pre-trigger, I can count for all that, and that's what we're going to set up. So now that we have a pre-trigger, oop, I don't want that much pre-trigger. Let's just do apply suggested again and raise our trigger level. Okay. So the software has already set that up for me. I'm good to go with my trigger levels. Next, we'll look at bandwidth and make sure we have the appropriate hammer. Okay. So I'll hit start here and I'll just take a couple hits real quick. Okay. So I just took a couple hammer hits and let's talk about what we're looking at. So if we start in this, let me move this guy and remove this guy. Remove. Okay. I'm going to switch this to dB. And I'm going to move this double cursor up to the start of my force level. And let's talk about why I'm doing that. All right. So what we're looking at here is the force input. And one of the nice things about the hammer is it's a brief transient event, a good click, so to speak. And transient events, when we perform an FFT, give us a nice broad frequency response. So when I hit something with this impact hammer, one of the reasons it's used as this tool is I'll get a nice flat force input over a given frequency range. Now it's not perfect, that force dissipates or rolls off over that frequency range, and that's what we're looking at here. So what this is my force roll off. And if you've done a modal test in the past, you might hear something like, I want my force input to be a 3 dB roll off or a 6 dB roll off. And this is what they're talking about. They're helping you or giving you guidelines for picking the right hammer or the right hammer tip for your force excitation. So with this particular hammer on the structure that I just hit, I have for a 10 dB roll off, I am good in a frequency range out to about 1300 hertz. And so if I come over here and I look at the response or my accelerometer, which is at this graph, and I move this cursor out to say 1300 hertz or about that same range, these are all the peaks that I satisfy with that roll off requirement, which means if I want to kind of take a look at anything past that, any of these modes out here, I need a different hammer tip or maybe a different hammer to appropriately excite that with the force requirement that we just talked about. And the nice thing with our software is we can look out to 4 times the bandwidth. So if there was anything way out there in the frequency range, past what we have set, we can come back here and look at the different hammer tips that we might need to appropriately find that. All right. So far we've set our trigger levels. We've verified that the hammer is good for the frequency we want to look out to. Let's move to the next thing, which would be windowing. Okay. So windowing helps us to, again, make sure that we're collecting the data in a good manner. So again, I'll hit start and I'll take a couple hammer hits and explain this as well. Okay, so I just took 3 hammer hits real quick. I'll hit stop and let's talk about windowing here for a second. So again, I've got the time response or the time data of those impacts. So I hit that with my hammer. You can see in the time domain, this is what it looks like. This is my hammer, this is my accelerometer. And what we want on the accelerometer side is a nice flat line that we start with, and we want that to end with a nice flat line within our time window. And our time window is going to be dictated by our bandwidth and our spectral lines, or our frequency resolution. So if I set this spectral lines to a higher number, then it's a finer resolution, and that finer resolution requires more time data to calculate the FFT. Okay, so the reason I point that out is with this setting, my acquisition time window is 0.32 seconds. Now, if I was in a situation that this particular structure didn't settle back down or return back to 0 within 0.32 seconds, I could come back in to this setting here and increase my spectral lines, and that increases my acquisition time. So now if I were to take data, I would now allow this structure 0.64 seconds to return back to 0. Okay, so that's one way that I can take care of this. If I don't want to change my spectral lines, I can apply something called a window. And to do that, I just drag this cursor down and you can see the shape of the exponential window that I'm applying. Now, when I apply a window, okay, so I'll drag this down, you can see how that window is going to affect this data. And now graphically, I can see as well how it's going to affect the data. So this applied window visually is the green line. And if I look at the force amplitude, when it's unwindowed, I'm at 3.95, and when it's windowed, I'm at 3.85. For my response, unwindowed, I'm at 69.58. Windowed, I'm at 67.7. So there's a couple things that happen when I apply my window. First, I'm introducing some false damping into my system because I'm saying it's calming down or ringing out before the end of my acquisition time. And I'm also kind of changing that force input. So if I apply a window to my test immediately becomes something that I cannot use to correlate with an FEA model. Okay, so an FEA model is expecting a specific damping value, and if I kind of force that damping value, I'm changing the structure that was analyzed. So my goal here is to not apply a window is the main takeaway. And there's some things in the software that I can do to make sure I don't have to. Lastly is the driving point survey. So here we would do just like we talked about. I could take and move my accelerometer and my hammer to different locations. I've already kind of done that here. So I've hit 3 different locations on the table that I'm measuring. And if I go back to Navigator after taking that data, I can plot those lines. And you can see kind of where they all are. Oops, I don't want to zoom in there. And you can see specifically that when I do a driving point at my second location that I've selected, I'm missing some excitation along the way, all right? And also with the blue line, I miss this mode. So what I may need to do is some more driving point surveys or hit some more driving points on the structure to see if I can excite all those modes with a given input. And if I can't, then maybe I need to pick more than one input or more than one driving point for this structure. And that's the type of information I get from that driving point. So after I've gotten through everything on this impact setup tab, I can go right to measure. A nice thing in our software is I've got this geometry feedback to show me where it thinks I'm hitting right out of the gate. Okay, so here's a graphical representation of my structure that I'll use to animate mode shapes. I can say, all right, table 5 is where I'm going to start. Minimize that for now. And then I will start taking data. And we'll hit 3 times. That's how many averages we're looking at. Okay, so there's my first hammer hit. And let me talk about this for just 1 second. So I've got my first hammer hit. I've got the time and FFT of the hammer right here. And then I've got the time and the FFT of the Excel in this second quadrant. Down here, I've got the instantaneous FRF, which means this is my hit 1 of 1, and then my averaged FRF. This last graph down here is my coherence. And, you know, it doesn't look great to the naked eye, but if I look at my range, it's at 1. So let's make that range just a little bit different. So I'll say from 0.8 to 1.1. And I've got this nice flat line at 1 the whole way. Now, the reason I've got a coherence of 1 after 1 hit is coherence is an averaged function. So this coherence doesn't even start to make sense until I hit with a second time. So if I hit a second time, now I've got some meaningful coherence. So if I, again, set these ranges to free, okay, now I've got some coherence and it still doesn't look that great. Let's come here and make these ranges free as well. Okay, now I've got some coherence that's kind of creeping up to 1. Let's take a couple more hits. Okay. All right, so the software thinks I did a good job. My coherence, I'm not overly excited about. There's some forces here, obviously, in my structure that are not the best. I've also got a double hit here and there. So let's go and do some all settings here that'll help me. So I'm going to auto reject with overload. I'm going to detect a double impact. I also said roving Excel was the best, so I'm going to change this to roving Excel. And I'm going to auto increment. And what that means here in a second is I'll tell you some things in our software that really help with this. All right. So now that I've turned those on, I'm going to start over again. So I'm going to hit start. I'm going to redo this one. Oops, double impact detected. So we're going to throw that out, and it's going to throw that out for me. Okay, there's a good hit. My coherence is much better now. Oh, another double impact. And let's do it again. Okay. And we're doing 0.6. There's an overload. Okay. So we've got some good hits and some bad hits. But let's see what kind of data we got. So I'll hit stop here. There's a lot of clapping and a lot of bells going on. All right. So let's go and just look at this in terms of animation. So we hit 2 points. We completed 2 measurements. So I've just got a modal matrix here that is 2 rows and 1 column. If I hit play here, we just measured 2 points. So if I go to the given frequency location, I can hit pause. And I can hang out here and see what's happening. And you can see I only measured the middle points of my geometry. I can also come over here in my animation settings and do something called automatic. Turn that on and off. Okay. Or I can go here and say none. Okay. So there's some different settings I have to expand kind of that geometry. Okay. Let's go back to geometrical, where it kind of brings everything together. All right. And what we're doing here so far in terms of modal analysis, which we're about to talk about in the presentation, is something called peak picking. Okay. So all I'm doing is moving this, even with the 2 points that I've measured, is moving this cursor from peak to peak to see the different modes and how they might be behaving. So let's talk about what we do in the analysis side for a little bit. All right. So now post-test, after we've collected data, we want to do something called modal curve fitting. And what we've done so far is looked at our structure, and we're assuming we have good high modal separation, which means there's no, when I move that cursor and look at each peak, there's no influence from a surrounding mode. Okay. But if my peaks are not well separated, I might have contribution from the surrounding modes. Okay. So if I were to peak pick in this particular scenario, and I only wanted to look at mode 2, which is represented by this red line, I'm going to have contribution from mode 1 and 3 because they're right there close and almost on top of that second mode. All right. So the reason that we do some curve fitting that we'll talk about here in a second is to separate these closely spaced modes. Okay. And we're going to do something called modal parameter estimation that I'll show you in the software. But the idea behind it is I'm going to pick a modal order. And so when we do something called curve fitting, if we think of kind of this basic example of curve fitting that's being illustrated in front of us, we'll have some data points. And a lot of times we'll use something like Excel to curve fit the data. And the more I tell it to go up in order, the more accurate it gets. But if I tell it to go too high, as you'll see when we get to like an 8th, 9th, or 10th order with this particular data set, is it starts to introduce some bends or some curves in this curve fit that are actually false, especially in that 10th order, right? So first order and second order aren't high enough. Third order gives us a good fit. Fourth is better. Fifth is better. But once I get too high, it starts to identify some bends that aren't representative of the data that we took, okay? And we'll see how that relates to the curve fit that we do here. Now, the way the curve fitting does is it's gonna look for a number of modes. So just like we went through with that curve fitting example in the previous slide, we're gonna say, curve fitter, look for one mode. And in this case, it'll say, okay, I found a mode, and this is the frequency it's occurring at and the damping value associated with it. Then it's going to go up to the second order, and it's going to look for 2 modes. And so it finds these 2 modes at 25 hertz and 75 hertz. Then it'll jump to 3, so on and so forth. And as it repeats a given mode, it'll look at it and say that's a stable pole. And you'll see this here in the software. Okay. So this is a graphic illustration, kind of a screenshot of what we're about to see in the software. It's going through this model order. And so again, at this first line, it's looking for 1 mode. Then here it's looking for 2 modes, all the way up to say 20 or 15 or 20 modes as a guess for how many green lines we have here. And these S's correspond to stable poles. And you'll see some other letters and what they correspond to as well. So there'll be some F's and some D's. Frequency and damping values are repeated in that model order. And you'll also see some O's, which means the origination of a new pole, and also V, which means a vector value is being repeated in that given calculation. All right, so let's look at that real quick for this flat plate that we did previously. So I'll go to some analysis. And this is that flat plate with a completed test. Let's look over a given frequency range. All right, so we're selecting this, and we'll do that stabilization. Okay, so here's that stabilization diagram. You can see here there's a couple modes that look pretty closely spaced. And then we've got some other modes that are showing up. Now, what we're doing here for this model size is 32. And just to drive home that example, let's say I said there was 100 modes in this data set. It would go through that calculation, and it's looking for 100 modes. And notice that we've introduced some stable poles or maybe some modes that are actually false, just like in that curve. When it got up to a 10th order curve fit, it was adding some bends in that data set that weren't representative of what we actually took. So a lot of times when you're doing this curve fitting, you'll want to start with a model size, the lower the model size. So, you know, if I'm back at 32, that looks a little more representative of what I'm looking at, okay? Once I've done this curve fit, I can go through and I can start to pick these stable poles. But my first question here is there really two modes at this one peak? Well, because of the way that the data was taken here, one thing I can do is come back here and click on something called a mode indicator function, right? Now I'll get a mode indicator function for as many inputs as I have or as many references as I have. And for this plate, what we've done is we've hit 2 different driving points and taken data at 15 different locations. Okay, so we've got 15 different FRFs, and those 15 different FRFs are calculated at 2 spots. So we really have 30 measurement points. All right. With those references, each reference gives me what's called a mode indicator function, and a mode indicator function will dip everywhere there's a mode. And if you look here, we've got 2 mode indicator functions, and both of these mode indicator functions dip at this one peak. So that verifies there's actually 2 modes there. And that's something called a repeated root. So if I go to shapes and I look at these 2 frequencies that are right next to each other, about a 1.5 hertz separation, I've clearly got bending, and I've clearly got, I clearly have torsion, and I clearly have bending, all right? But if I was doing peak picking, all right, so if we go to tools, add-ins, and let's do the time animation, just so I can show you why we wouldn't want to peak pick this. Okay. Let's say I went here and I just did a peak pick at that given frequency, which was about 135 hertz. I don't really have torsion and I don't really have bending. It's a combination of those 2 modes, okay? So let's look at this. I can't really discern the 2 modes I was able to discern by doing the curve fit here and clearly identify bending and torsion. So that's why the curve fitting is more of an accurate way of getting those mode shapes discerned. Okay, so repeated roots, we talked about this. In our plate example, we had torsion and bending real close in frequency. When I have a symmetric structure like our plate, let's say we have a drum. When I strike this drum, you can see mode 1 and mode 2. They're both at 20 hertz, just separated by a fraction here, but the modes are different, okay? They're both of a flexible mode, and one is slightly different than the other, and only curve fitting would allow me to be able to discern this. All right, we talked about these mode indicator functions and how I get a mode indicator function for every reference I have, and it's a lot of times why we want to put more than one input into the structure. The mode indicator function will dip where there is a mode, okay? And it's used to detect the presence of these repeated roots. So just like this drum, we'd want to have more than one input, more than one reference, so that we could have some mode indicator functions to help us identify any of these repeated roots. Okay. We've got a few more minutes. I'm going to try and get through MAC here and explain that. So modal assurance criteria, or MAC, describes how similar the shapes are for a given mode pair. Now, I've got mode 1 and mode 1, and the correlation between mode 1 to itself should be 100%. So we have a MAC correlation of 100%. In mode 2 to mode 1, they're 2 very different modes, so the correlation or the MAC value should be very low, and it is, okay? These 2 only correlate by 1.5%. Now, if I didn't measure with enough points, okay, So previously we were looking at 15 points on a plate. Here we're looking at 6 points on that same plate. And I've got mode 7 at 764 hertz and mode 3 at 385 hertz. And the MAC correlation, even by looking at these, they're very similar, but the MAC correlation is at 96%. That should not be the case. We should not have the same mode repeat at two different frequencies, okay? So something's off with our data. Those same modes at those same frequencies with 15 points on the same structure are clearly identified. And if I just look at the 6 points and I kind of go back and forth real quick, and just use your eyes to focus on those 6 points between these two measurements, you can see the 6 points on the 15-point measurement and the 6 points on the 6-point measurement are moving the same way. But because the 15 points give us more resolution here, we are able to discern these mode shapes. So the MAC helps us with that. On the diagonal, the MAC should be 100%. We're comparing mode 1 to mode 1. That should be 100% correlation. So everything we're mode 2 to mode 2 and mode 3 to mode 3 on diagonal should always be 100%. It's the off diagonal that we want to be close to 0. That shows us that we are correctly identifying mode shapes, okay? So this is a good MAC matrix that shows us that the off diagonals are low, all right? So if I go back here to our analysis and I go to modal validation and I look at matrix geometry, sorry, I want table. Hold on with me. Table geometry, and I do my MAC. We actually want to look at a full modal analysis. And let's do matrix geometry. There we go. Oh. There we go. We'll fit this. And you can see here, if I click on these, mode 1 to mode 1 is good, 2 to 2 is good, and all these off diagonals, I was able to clearly identify different mode shapes. All right, so that MAC matrix helps us do that. And as long as we've correctly picked the modes, we can also go to our modal synthesis and look at this as well. So this is another way to correlate that we've done good modal analysis and picked all the modes. So we've got the first 8 modes out to approximately 800 hertz, and I want these curves to overlay. If I didn't pick the right modes, so let's say I got all these modes but missed mode 4, and I missed mode 3, this green line is based on the mode shapes I was able to solve for. And the red line is the actual sum of the FRFs acquired. If I didn't pick all the modes, then my modal synthesis or my synthesized curve does not overlay well with the actual data. Okay. So that's one way I can verify that I've done a good curve fit. All right. Now we can also do something called modification prediction. So in our test, available in our software, is something where if I wanted to make a change to the structure, I could do that in the software, in the test software, and see how that affects the curve. And I think Charles actually has a video ready for us to go on that, if there's time to show that, Charles.
Test lab modification prediction can be used to apply modifications to experimental modes. To turn it on, go to Tools Add-ins and select Modification Prediction. This uses 23 tokens if you have test lab tokens. Here we see our twisting mode, and one of the modifications we may consider is adding stiffness to prevent it from twisting on this vehicle body. So we can go to Add Spring Damper here, select 2 points, enter a stiffness, And we might do that again because we got a bit of an asymmetric stiffness being added here. Perhaps we want to add a second stiffener. So we'll do that on the other side here. Pick the 2 critical points, add the stiffness. Now we have 2 stiffness elements that have been added to the vehicle in order to increase the torsion modes. So now we can go to predict modes here. We can type in twist for our predicted mode set, hit calculate, and then we can look at the FRF at these key points, like on the pillars of the vehicle, and we can see that we've increased the stiffness and increased the frequency of that main mode. If we look at the original mode, it was at 27.049 Hertz. The new mode is not at 27.39, that remained about the same, but the new mode went all the way up to 27.816 Hertz. So we increased the frequency almost a full 1 Hertz. If we look at some of these other modes that we have here, there is a roof pumping mode. And for that, instead of trying to use stiffeners to affect the modal frequency, we might consider using something like a tuned absorber. To use a tuned absorber, we can simply pick Add Tuned Absorber here. We pick the point we would like to add it to in the Z direction. Perhaps we'd like to add about 6 kilograms of mass or no more. We're going to target 27 Hertz or so. We'll hit Tune here to optimize it. And now we have a tuned absorber modification on the roof pumping mode. You can go to predict modes here. We can see that we've taken the original mode and split it in 2 and really reduced the motion at the original frequency.
Yeah, that was it. That concludes our presentation today.